Okay, so last time we have learned hydrostatic forces on submerged plane surfaces. So today we are going to look at hydrostatic forces on submerged curved surfaces. So I hope by the time we finish this subchapter, you will be able to determine the variation of pressure in a fluid at rest, and then you can calculate the forces exerted by a fluid at rest on curved submerged surfaces. So basically, for a submerged curved surface, the determination of resultant hydrostatic force is more complicated or more involved because it requires the integration of the pressure forces that change direction along the curved surface. So it is quite hard. And also the concept of the pressure prism in this case is also not much help either. It will not help you much because of the complicated shapes involved here. The easiest way to determine the resultant hydrostatic force, Fr, acting on a two-dimensional curved surface is to determine the horizontal and vertical components, Fh and also Fv, separately. So how we want to determine this? We can use the same method that we have learned on submerged plane surfaces. Basically, this is done by considering the free body diagram. So this is a sample of a free body diagram, or we can call it FBD. So this is also a sample of free body diagram, okay, and this is how it looks when we put it outside over here. The free body diagram of the liquid block is enclosed by the curved surface. We are going to have a curved surface, if it is a curved surface like this over here, and also two plane surface. So one horizontal, so this is the horizontal plane surface, and another one is the vertical plane surface, so this one. Okay, so the forces acting on the imaginary planes, so this is an imaginary plane because there are no plane over here. You just imagine there are a plane here. So the forces acting on the imaginary plane can be determined using the method of hydrostatic forces on submerged plane surfaces that we have learned before this. The weight of the enclosed liquid block of volume. Okay, so we have a liquid block over here. There are weight of the liquid block because the weight of the liquid itself. To determine this, we can use a simple equation which is W equals to rho GV. Okay, and then using this, we know what type of liquid it is, we know the gravity, we can also calculate the W if we have the volume. Okay, it will always acting downwards because the gravity is acting downwards. Okay, so there are no W that acting upwards. Noting that the fluid block is in static equilibrium, so we know that this is in static condition, the fluid does not move. Okay, the force balances in the horizontal. We have the horizontal and vertical direction, the force will balance. Okay, if we look over here, Fy, NW, and also Fv is the type of forces that acting in the vertical direction, and then we also have Fx and Fh acting on the horizontal direction. So from this we know that Fh is equals to Fx, Fv equals to Fy plus W, and this plus value is plus because the direction is the same. So the direction is the same, so the value will be plus. If the direction is different, for instance, we have when we have the fluid is above the curved surfaces, like this. Okay, so when it is like this, so our Fy is acting upwards and our W is acting downwards. So when this happens, so this one will become minus, because the force is acting in the opposite direction. Hydrostatic force acting on the curved surface, so this is called Fr. Fr equals to Fh square plus Fv square, and then it is square root. Then we will get the value of Fr. And the tangent of the angle it makes with the horizontal is tan alpha equals F vertical, force of vertical force, over force of the horizontal force. Okay, so this is the angle. The exact location of the line of action of the resultant force can be determined by taking a moment about an appropriate point. Yeah? These discussions are valid for all curved surfaces, regardless of whether they are above or below the liquid. Please remember that if case of a curved surface above a liquid, okay, when a curved surface is above the liquid, so like this is an example of a curved surface above a liquid, because of the Fy and the W works in opposite direction, please remember to subtract the value from the vertical component. Okay, when the curved surface is a circular arc like this is an example of a circular arc, full circle or any part of it. So if the circle is a full circle of like this example, this is a half circle. The resultant hydrostatic force acting on the surface always passes through the center. So as you can see here, if it is a complete circle, it always passes through a center. Yeah. Thus, the pressure forces form a concurrent force system at center, which can be reduced to a single equivalent force at that point. So we can also reduce it to a single force at that point. So this is Fr. And finally, the hydrostatic force acting on a plane or curved surface submerged in a multi-layered fluid. Okay, if the fluid is not consist of one type of fluid only, for this example, we have oil and water. So this is a multi-layered fluid, of different densities. It can be determined by considering different parts of surfaces and different fluid as different surfaces, finding the force on each part and then adding them using vector addition. For instance, so we want to look at the total of resultant force. We should just add this plane as one plane and the below plane is another plane. So we just calculate Fr for one plane and we add another Fr for another plane. So if we want to find Fr equals to Fr1 plus Fr2. Okay, and it is also equals to P times A lah. Okay, so equals to P1 A1 plus P2 A2. So it's easy like that. Okay, so I think that's all. And after this, we will look at several examples, and you can try and answer them on your own. And if you can't, there are videos for the calculation uploaded inside the Padlet and also in Google Classroom and also in Highland. You can choose whether to look at them or you can answer them by yourself. Okay, see you again in next class. We will learn the buoyancy and stability.